discussions on vibrations of beams, we have till now looked at only straight beams. However, there are various places you find curved beams. For example, in arches, in bridges, also we have rings which can be treated as beams which are curved. So, today we are going to initiate some discussions on the dynamics of curved beams. So, today we are going to look at essentially the modeling aspects of a curved beam. Now, the first and the fundamental difference between a straight beam and a curved beam that we will see is, because of this curvature, the axial motion or the circumferential motion is coupled to the transverse or the radial motion of the beam. So, there is a coupling between these two directions. So, we can no longer treat using one field variable for our deflection. So, we must use two field variables, one for tracking the circumferential or the axial motion, and the other is for the radial motion. So, as with any beam theory, we are going to make some assumptions to simplify our modeling process. So, the first assumption So, the first assumption we make is that this whole the curvature of the beam is So, we will look at a very special situation where the curvature of the beam is a constant and the beam is planar. So, the second assumption we make is the deflection is also planar. Thirdly, we will assume that the deflection is small. Compared to the thickness. Compared to the thickness of the beam, the deflection is small, and we also assume that the thickness itself is small compared to the curvature. Finally, we assume that the Euler-Bernoulli hypothesis holds. And we, along with that, we say that there is no shear. So, under these assumptions, we are going to model a curved beam. So, we are going to restrict ourselves to the case of a beam with constant thickness. So, let us consider So, here I have drawn a ring really, but it could be a part of a ring. We consider a small element of this ring, so this is the radial direction and the field variable will be indicated by w theta comma t, and this is the theta direction where we so the radius of this circle, the dashed circle, which we will consider as the neutral fiber, that has a radius r, which is constant as we have assumed. Now, let us look at this little element. Now, we are going to look at the deformation kinematics of this little element. So, let me draw. So, when you consider the deformation kinematics, you can understand that. So, this is at an angle theta and the small, this is the small angle d theta. Now, initially the length of any fiber in this element at a height z so the length of this fiber before deformation let me indicate this by ds is we are looking at a fiber which is at a height z from this neutral fiber. So, ds, the length of this fiber before any deformation, is r plus z times d theta. Now, when this element deforms, now you can imagine that you can consider this deformation in two steps. One is its axial elongation. So, this moves from, so any point which was here moves here. So, this angle is nothing but u over r. So, u is the deflection of the of this point in the circumferential direction. So, as we have mentioned that, so this is u. The second deformation that can take place is that this deflects out radially. So, let me draw that first. So, here is P 2, and now here is P 3. So, this point P 2 moves to this point P 3. Now, here again there is this angle which can now be written like this, that this is the slope of the center line of this element when there is a deflection in the radial direction or the transverse direction, and which is captured by this field variable w. So, del w del theta 1 over r. So, that is nothing but the slope of the center line, because w is the deflection of the neutral axis. So, that multiplied by z, z is the distance of this point from this neutral fiber. So, this times z is the deflection. So, this is nothing but the angle. For small deflections, we know that this is the angle times the radius gives the linear deflection of point P. So, it goes from P 2 to P 3. So, essentially this linear distance is what is being measured by this quantity, and when you divide this by r plus z, that gives us this small angle. So, therefore, now when you combine these two deflections, then the total angle. So, this line went from here to here, and now this line has travelled back. So, this angle, let us say, is theta prime. Then theta prime is given as theta plus u over r because of this motion, circumferential motion, and minus this angle. So, that is theta prime. So, therefore, after deflection, d s prime, if we call it d s prime, then that is approximately this is r plus z plus w is the transverse or the radial deflection. So, that is the new radius times d theta prime. So, we have to calculate d theta prime. So, that turns out to be d theta plus, since r is a constant, so del u del theta times d theta minus so that so this is the expression of d s prime, and therefore, if we calculate the strain now, in that fiber at height z from the neutral plane, that can be calculated as d s prime minus d s over d s, and if you do this calculation, it turns out to be and which can be approximated by considering that z over r is much smaller than 1. So, you can take this r and this write this as 1 plus z over r and take into the numerator, and you leave out terms which are quadratic in z over r. So, then it can be simplified So, that is the strain in the fiber. Now, using this strain, we can use Hooke's law to write the stress as Young's modulus times the fiber strain. So, that is going to give us the stress in the fiber. Now, these stresses can be integrated over the cross sectional area of the beam to obtain the force resultants. So, let us calculate the various force and moment resultants. So, let me first draw out this free body diagram of So, this is a little element, and we have the shear force on this face, the bending moment and the circumferential forces. Now, let me calculate this these stress resultants. So, n is nothing but integral over the area stress times the area, and if you substitute these expressions and calculate this, it turns out to be since there is a z term here. So, when you integrate over the area, since this is already measured from the neutral fiber. So, this term will vanish. So, you are left with this. So, this is the expression of the normal force on the face. Then we have this bending moment, which is once again we calculate as we did for the beam. Now, because of this additional z, this becomes z square, and that makes it an even function. So, and whereas this becomes an odd function, that cancels off. So, you are left with contributions only from this term. So, that is the bending moment. Now, using and the shear force, as I have mentioned that we do not consider shear. So, it is infinitely rigid in shear. So, that will come out from the equations of equilibrium. So, let us now start writing the equations of equilibrium. So, first we will write the circumferential equation. So, that reads, so rho a is mass per unit length. So, r d theta is the small length of that element. So, this is mass of the little element times u is the circumferential motion or the field variable. So, the acceleration, and that must be equal to the forces in the circumferential direction. So, let us refer to this figure once again. So, in the circumferential direction we have, so n theta plus d theta can be written as n plus del n del theta into d theta, and this minus, so this into cosine of this small angle. So, that is small. So, that is taken as 1 minus n because of this, plus because of the shear force. For example, here it is this into sine of this small angle, which is d theta over 2. So, that is almost d theta over 2, and plus we have this again so therefore, if you divide by d theta and drop terms smaller than the first order, then you can easily write this equation. So, this is the equation of motion for the circumferential in the circumferential direction. Next, we look at the radial direction. So, once again rho a r d theta is the mass of the little element times the acceleration in the transverse or the radial direction must be equal to the summation of all forces in the radial direction. So, this is what we have. So, I can write this as V then there is this normal force which is towards the center, and so this negative, and there is a projection. So, these are the forces in the radial direction. So, that implies so this is the equation of motion in the radial direction. Next, we will look at the rotational dynamics. Of this element. We will neglect the rotational inertia of this element. So, in that case this equation actually boils down to only moment balance about the center of mass of this element, which can be written as so m is this moment and we have two contributions from these shear forces about the center of mass. So, that can be combined and written as so this is r theta over 2 and this is also r theta over 2, and they produce moment in the same direction. So, it is v times r d theta. So, that must be equal to 0. So, that implies so that is what we obtain from moment balance. Now, we are going to combine these equations. So, essentially we are going to eliminate this v and also replace this n. So, if you do that, then you get the equations of motion. So, these are the equations of motion for the beam with constant curvature r. Now, next we will also look at the variational formulation for this. This we will need when we do approximate calculations using for example, Ritz method. So, let us look at the variational formulation. So, we start with by writing the kinetic energy. Is 1/2 the mass of the little element times the velocity square. And this integrated over the full beam. So, that is the kinetic energy. Similarly, we now derive the potential energy. Which is nothing but half. Now, we know from theory of elasticity that the energy per unit volume is stress times the strain. So, 1/2 stress times the strain for linear theory. So, stress is Young's modulus times the strain and so this is per unit volume. So, we integrate first over the area and then over the length. Of the beam. Now, we will substitute the expression of this epsilon and that turns out to be. So, then V So, this bracketed term is the strain epsilon. So, that squared dA and this and there was one 1 over r in the strain expression. So, that becomes 1 over r square. Now, if you square this these terms. So, this will give w plus del u del theta whole square, and that when integrated over the area. So, these terms will have nothing to do with the area. So, it is the area itself. So, we have so so that is the contribution from the square of this term. Then there is a square of this term. So, you will have z square, and you have r power 4, and here there is an r. So, that will give 1 over r cube, and z square integrated over the area, that is going to be the second moment of the area. So, the square of this second term is going to give us then there is this third term 2 times this into this, and that is linear in z, and when you integrate over the area, since z is measured already from the neutral axis or neutral plane. So, that term vanishes. So, these are the terms in the potential energy expression. Now, to move on further, before we move further, we let us make a little bit of simplifications using certain redefinitions. So, let me redefine time like this. So, this is a non-dimensional time tau, a non-dimensional circumferential displacement and a non-dimensional transverse or radial displacement w tilde. And I will also define the slenderness ratio, which will be I will define like this. So, the radius of curvature of the beam divided by the radius of gyration of the cross section. So, that reflects the slenderness of the beam. Now, if you use these expressions, then the Lagrangian can be written as, so integrated over the length of the beam so this is tau So, that is the Lagrangian of the system. Now, we use the Hamilton's principle to derive the equation of motion. which says that this must vanish, the variation of this Lagrangian of this action integral must be 0. So, if you do that, then using the expression of the Lagrangian that we have just now derived, I will drop the tilde in these calculations now. So, this must vanish. Now, this has to be integrated by parts with respect to time, these two terms, and here we have to integrate by parts with respect to theta in these 3 terms. So, if you do that, then finally, when you get the boundary terms and the variation over the domain, so this is this integral. So, here you have the limits over the domain of the beam. So, it is 0 to some angles, let us say theta bar, and plus So, this is what you will obtain. Now, from here it is easy to see that this using standard arguments we can see that. So, this integrand must vanish and similarly this integrand must vanish, delta u and delta w being independent. So, we have the equations of motion So, these are the two equations of motion which we have derived earlier as well in a slightly different form. Now, you can once again see the coupling between the circumferential and the radial directions. Now, here since this is non-dimensional, these equations are non-dimensionalized, you can look at the contribution of these terms in the equation. Now, if the beam is very slender, which means slenderness ratio is very high, then these terms will become insignificant. In that case, the equations will get simplified. So, you have only 3 terms in each equation, which you can then try to solve. But if the beam is not so slender, in that case these terms will also contribute to in the dynamics. Now, let us look at the boundary conditions. So, they are obtained from so from boundary terms we have at theta equal to 0 and theta bar, so we must have this equal to 0 or u must be equal to 0. So, either the circumferential motion is restricted or so which is a geometric condition and this is a natural boundary condition. Similarly, at again at theta equal to 0 and theta bar, so this or so these two boundary conditions follow from these boundary terms. So, this is the first boundary term and this is the second boundary term corresponding to displacements. So, delta u and delta w. There is this third boundary term which is in terms of the slope. So, once again at theta equal to 0 and theta bar, del u del theta. So, this must be equal to 0 or the angle must be equal to 0. So, you have these boundary conditions. So, these are the geometric boundary conditions, whereas these boundary conditions are the natural boundary conditions. So, now in case of a complete ring, for so when there is a complete ring, the in that case you do not have boundaries like this. So, what you have is you have these periodicity conditions. So, which means that u at theta plus 2 pi must be equal to u at theta for all time, and similarly and all that follows from these periodicity conditions. So, everything is going to be periodic. So, displacement, slope, bending moment, shear force, etc. So, they are going to satisfy the periodicity conditions. So, for a complete ring we have these two conditions. So, let us briefly recapitulate what we have discussed today. We have today discussed initiated some discussions on the dynamics of curved beams. We have considered in particular beams of constant curvature, and we have derived the equations of motion using both Newtonian as well as the variational formulation. And this is very interesting and peculiar about these curved beams, that the transverse and circumferential motions now are coupled. They so in the straight beams we have only the transverse motion. We can treat the transverse and the axial motion separately. They are decoupled, but this curvature in the case of curved beams couples the circumferential and the transverse dynamics. That is what we have seen through the equations of motion. So, with that we conclude this lecture.